7.6 talks about integration by trigonometric substitution. So here we're trying to get rid of a radical, and radicals are very challenging to get rid of. One way of getting rid of a radical, of course, is to try to u sub, but if that doesn't work, if you see one of those three, then I'm providing this on your test. You don't have to memorize that. If you see a number minus x squared under a radical, you could let x equal a the sine of theta. If you see a square minus x plus x squared, you let x equal a the tan of theta. And if you see x squared minus a number, you let x equal a the secant of theta. And you're going to make use of those two for this. And you're going to make use of either this or this for those two. So we start off with example 1a. So I try the u sub, that doesn't work. And this is not something that I know. In that case, I see a radical and I see an x squared minus a, so I know it matches 3. I would let x equal a. What do you square together for? 2, the secant of theta. And I would take a derivative of that. That will be twice the secant of theta tan of theta d theta. So I go in and I make my substitution. I think I'm going to need more space. That's never a problem. So my x is right there. I have twice the secant of theta, and there's this radical, and there's twice the secant of theta squared minus 4. And dx is really all of this. That's twice the secant of theta tan of theta d theta. The 2's cancel out in this case. That's not always the case, but good start. So, and I know that this secant right here will cancel with that secant. I'm left with the integral of the tangent of theta d theta divided by, now this radical I'll work on the side, and that's where these are going to come in handy. That is really 4 the secant squared of theta minus 4. If you factor a 4, that will be secant squared of theta minus 1. And we know secant squared of theta minus 1 is nothing more than the tangent squared. So that will be the square root of 4 the tangent squared of theta. And if I substitute that back in, that will be twice the tangent of theta d theta. And that would be 1/2 the integral. And here those cancel out. Again, it's just a coincidence. And that would be 1/2 theta plus c. But as you know, we did not start the problem with a theta. We started the problem with an x. So this is something you have to do on every problem in this section. You have to go back to the original setting, which is right there. And you have to come down and say, well, x over 2 equal secant of theta. So theta equal the arcsecant of x over 2. And there's no way around this. You have to do this every time. You could, if you want, if you like, say that this is the cosine of theta equals 2 over x, and theta will be the inverse cosine. That really doesn't matter. That turns out to be an identity actually, but no need to worry about it. If I get to the next problem, I notice it's the same idea. That is, I see 3. I would let x equal 3 the secant of theta. Dx will be 3 the secant of theta tan of theta d theta. So my substitution would be, my u is going to go right there. So that would be 3 the secant of theta squared minus 9 underneath the radical all over 3 the secant of theta. And be careful, dx is all of this. That's not something to forget. 3 secant of theta, tan of theta d theta. Now, I'm going to take this 3 up front. I still have a secant of theta left. The top, the radical, I'll work out on the side. And actually, I could have canceled this, right? No need to carry that. That's good. And I could have canceled those as well. No need to carry that either. So what I have left, I have a tan of theta d theta left out of this. As far as the radical is concerned, that's 9 the secant squared of theta minus 9. That is 9 into the secant squared of theta minus 1. And I know that secant squared of theta minus 1 is the tangent squared of theta. So that would be 3 the tangent of theta. That's what comes out of the radical. So that is 3 the integral of tangent squared of theta d theta. And if I work that out, what do you take a derivative of to get tangent squared? No such thing. We dealt with this before. We know tangent squared is secant squared of theta minus 1 d theta. Now this work right here you're going to do every time, and it is that messy, and these problems are this long. And what this is going to equal, it's going to equal 3 times, what do you take a derivative of to get secant squared? Derivative of tangent is secant squared. Okay, you know what? Let me give it more space. This way, I'm not squishing anything or leaving anything out. So that is okay. So that is 3 times. What do you take a derivative of to get secant squared? Derivative of tangent is secant squared minus theta plus c. Almost done. That's going to be 3 times. I need the tangent of theta, and I need theta plus c. That would be my final answer. Do not leave your answer in theta. And this is the part you need to adjust to. You have to take the original setup. You're going to say, I had x equal 3 the secant of theta, which means x over 3 equal the secant of theta. And there's no way around this. I know it's unpleasant in the beginning, but since you're going to do this on every single problem, this is the hypotenuse over the adjacent. The hypotenuse over the adjacent. And if you want to figure out what this side is, use Pythagorean, right? That would be the square root of x squared minus 9. So what do I need out of this theta? I need the tangent. The tangent is the opposite over the adjacent. And what's theta? If secant of theta equal x over 3, then theta equal the arcsecant of x over 3. And similarly, you could say there, if you wish, cosine equal 3 over x, and write inverse cosine of 3 over x. It makes no difference. That's an identity that you're not responsible to know. I have 2 problems of each. One of them has a twist. I know you like the twist. So, and the twist comes up for us. That's why I'm doing it. If I look at the next set of problems, I notice those are backwards. Unlike the first 2 examples, that was x squared minus 4 on A and x squared minus 9 on B. Here I have it backwards. According to the first rule, I let x equal A the sine of theta. So here I would say, let x equal A, what do you square to get for 2 the sine of theta? And the x would be twice the cosine of theta d theta. So this is going to become the integral, and let's see. That's going to go in 2 places. I'm going to have twice the sine of theta, the square root of 4 minus twice the sine of theta squared. And again, don't forget dx is all of this. That is twice the cosine of theta d theta. So if I proceed, the 2's cancel out. I'm looking at the integral. There's a cosine of theta d theta at the top. There is a sine of theta in the denominator. Plus the radical. I'm going to work out the radical. That's the square root of 4 minus 4, the sine squared of theta. 4 into 1 minus the sine squared of theta. And that is the square root of 4 times the cosine squared of theta. So this radical right here will yield twice the cosine of theta. Those cancel out. That is 1/2 the integral of cosecant of theta d theta. And if you remember what that was, natural log of absolute value of cosecant of theta minus cotan of theta plus c. I need a bit more space. We have plenty of space. That is 1/2 natural log of, I need the cosecant of theta, I need the cotan of theta plus c. So I have to go back to my original substitution. The only way you could avoid this mess if you were given a definite interval, but we're not in this case. So what we'll do here, we'll take our original setup again, and we say, well, look, that means the sine of theta equals x over 2. And you draw the triangle. Again, you're going to get used to this. There's no way around it. If I take this triangle, make this just a bit more pleasant. There we go. And make this a bit bigger so we could see it more. So the triangle is always in quadrant 1. That's the good news. There's theta. Sine is the opposite over the hypotenuse. The opposite over the hypotenuse. If you want to figure this side squared, 4, I'm going to figure it out here. 4 equals x squared plus, call this side L. So you move that over to the other side and you square root both sides. That's the square root of 4 minus x squared. What do you want out of that? You want the cosecant. Cosecant is the hypotenuse over the opposite. And cotangent is the adjacent over the opposite. And unfortunately, there is no other way of doing this problem, but you'll adjust. A bit lengthy, not hard, just work slowly and you'll get to the answer. I have another one of those. If I look at this problem, I notice, oh, there are too many dx's. Okay, that's not working the way I want it. Got it. Okay, now, here I notice, well, I could try a u sub. I could let u equal x squared. du, or even better, 25 minus x squared. But let's go this route. U equal x squared. Du will be 2x dx. So before I proceed, I will break this up just to see what is going to happen. Would this benefit me? So I notice what I need. I need an x dx. Right? I need an x dx. So I take this and I save an x dx for my du. Right? And that leaves me with an x squared. So if I really make my substitutions correctly, x dx will be du over 2. Okay, I did it again. That would be 1/2 the integral of, and a du is right there. And x squared is my u. That would be u over the square root of 25 minus u. Now, I could try another sub. Let w equal 25 minus u. dw is negative du. And let's see how this works. This is 1/2 the integral. Now, my du is really a negative dw, and that's the square root of u, but I have a small thing to worry about. What does u equal? Right there. If I switch those, wouldn't that mean that u equal 25 minus w? And I did put a u down there, didn't I? Yep, I knew it. That's actually my w. So now if I'm glancing at this problem, I really don't need to use this section. You could start from the beginning. I'll talk about that in a minute. I could split this up. I could say this is 25 w to the negative 1/2 minus w over w is w to the 1/2 dw. And I could say this is negative 1/2 times 25, add 1 to the power, divide by that, add 1 to the power, and divide by that. Now all what I have to do is substitute w back and I know what w equal. W equal 25 minus u. So that is 25 minus u. But I know what u equals. U was x squared. And that would be my final answer. Now, I could have, from the beginning, I could have not done this, but that's going to be longer. I could have said let x equal 5 the sine of theta. So now you have a choice. Dx will be 5 the cosine of theta d theta. That will become the integral of the square root of 25 minus. In place of this, I'm going to put a 5 sine of theta and square it. Dx is going to be 5 the cosine of theta d theta, but I have an x cubed left. I have a 5 sine of theta cubed. You could do this if you wish. You should get to the same answer, but that takes more steps. So if I could use a u sub at any given time, I would. That's why we spent so much time on u sub. And there it is. Now the last one deals with the last case, or the middle case I should say, that one. So here, I'm glancing at this and I'm thinking, okay, that doesn't match anything I know. Well, I know there's a trick to it. Let x equal, what do you square to get 5? Radical 5 the tan of theta. Dx will be radical 5 secant squared of theta d theta. I don't like that secant. Secant squared of theta d theta. So this becomes the integral of, my u is right there. That is the square root of 5 plus radical 5 tan of theta squared. Again, there's my u. And dx is this whole mess. Radical 5, the secant squared of theta d theta. Now I take the radical on the side. It's a good habit to do. And if I take this and I square it, that's 5 the tangent squared of theta. Factor of 5 out, 1 plus tan squared of theta. And I know that tan squared of theta is the tan squared of theta plus 1 is the secant squared of theta. So this becomes the integral. The top is radical 5 secant squared of theta d theta. The denominator is radical 5 the secant of theta. Those cancel out, and this cancels one of those. I'm left with the integral of the secant of theta d theta, and that's why we had to do the trig integration before we got to this section. That's natural log of secant of theta plus tan of theta plus c. That is natural log, and I need to get a secant and I need to get a tangent out of this. So if I take the original setup, I know that tangent of theta equals x over radical 5. Get to my triangle again. Always in quadrant 1, that's the good news. There's theta. Tangent is the opposite over the adjacent. And this would be the square root of this squared plus that squared. It's not a coincidence that you get the radical in there every time. There's theta, opposite, so this is the square root of x squared plus 5. And what do I need out of that? I need the secant, the hypotenuse, over the adjacent plus tangent. Well, tangent is either you say it's the opposite over the adjacent or it's right there. And there is no other way to do this specific problem. So you have to adjust to these things. Kind of long. The only way you could avoid this substitution, if you have a definite integral like we do right here. That is, I glance at this problem. This problem has a small twist. So here, why is that highlighted? If I look at this problem, I see a radical. Radicals are very hard to get around. You really can't shake a radical. So the way to do that is for you to complete the square and use one of those 3 properties. That's x squared plus 2x plus a number. So take half of the middle number and square it. That's a 1. I have a 5. If I took a 1 out of it, I have a 4 left. So that makes this x plus 1 squared plus 4. So that's the square root of x squared plus 1 squared plus 4. If I come in and I let, what's taken the place of x? X plus 1 equal twice the tangent of theta. You could let u equal x plus 1, and you will be dealing with u squared plus 4, and let u equal twice the tan of theta if you wish. But if it's linear, you could pretty much jump that way. You know what? I could go for a u, but that's going to be longer. Now, when I proceed and take the x, that is twice the secant squared of theta d theta. So this is the integral of this is twice the tan of theta squared plus 4 underneath a radical. dx is all of this. That is twice the secant squared of theta d theta. Now, since I have a definite integral, it would be very wise for me to make use of it. Put a negative 1 in for x. That's 0. 0 equal twice tan of theta. So tan of theta equals 0. That's when theta equals 0. Put a 1 in there. 1 plus 1 is 2. 2 equal twice the tan of theta. So tan of theta equal 1. That happens at pi over 4. This is the one time I don't have to go back to the triangle. I just have to clean this up a bit. 0 to pi over 4, twice the secant squared of theta d theta. So now I don't need to go to x anymore, but I need to work out that radical. That's the square root of 4 tan squared of theta plus 4. Factor a 4 out. And tan squared of theta plus 1 is secant squared of theta, so that is twice the secant of theta. Those two cancel out. That is, and this cancels one of those, that is the integral from 0 to pi over 4 of secant of theta d theta. Well, I know what that is. I just worked out that problem. That is natural log of secant of theta plus tan of theta evaluated from 0 to pi over 4. If I throw the pi over 4 in there, that is radical 2, and that is a 1. And if I put the 0 in, secant of 0 is 1. That's 1 over cosine minus 0. So the 1's cancel out. I'm left with natural log of square root of 2 as a final answer. And that pretty much does it for this section. Let me just write this a bit nicer. Square root of 5 over 5 square root of x squared plus 5 over radical 5 plus x over radical 5 plus c. And that would be it for this section.